Yeah, so share your views with me. I have 26 of you, Forsen, Abbas, Adele, Banasco, you are all here. So what is dimensional analysis? Anybody to share what he or she can recall in school? Anybody? Okay, Stephanie. Stephanie, break the ice for us. When we talk about dimensions of a physical quantity, what do we mean? Dimensions of a physical quantity. What do we mean? Yes, Meredith, if we're let's hear from you.
Okay, so dimensions of a physical quantity is an expression of the relationship between the physical quantity and the fundamental quantity of mass, length, and time.
So expression of the relationship between the quantity, the physical quantity, and the fundamental quantities, mass, length, and time, right? Okay, so thanks for the contribution. Let's have another view. The ladies seems to have started with us. What about my gentlemen? The gentlemen, what do you also have to say about dimensions of a physical quantity? Yes, Dari.
Dimensions of a physical quantity. They denote the physical nature of quantity in terms of the fundamental units.
All right, thank you so much. Thank you so much. So we talked about dimensions of a physical quantity. What then is a physical quantity? When we say that a quantity is physical, or the term physical quantity, what do we mean? What is a physical quantity? Hey, there again. Let me. There's another hand up. Let me. Oh, the same two hands. Oh, I need more hands. I'll come. Okay, Inshiraminta. Inshiraminta, what is a physical quantity?
So a physical quantity is physical property that can be measured either by instrument or calculation using an appropriate equation.
Or instrument, using an appropriate instrument. Okay, so yes, okay. So Ishra, thank you so much. So when we talk about a physical quantity, any quantity that can be quantified or measured. Example of physical quantity. Any quantity that can be measured or quantified. Elom. Yes, I can see yes, more sir. Hands. Elom, start with us.
Sir, please, length. That's the distance between two. That's the distance between two points in space.
Elom, you are right. Isabella, another example of a physical quantity.
Pressure.
Mass.
Pressure.
Pressure. Okay. Melchizedek. We are in class, so come again.
Amount of substance.
Amount of a substance. Prince.
Time.
Prince. Time. Good.
Simplify.
So you are right. So we can talk about a lot of quantities that can be measured. Okay. Then we can talk about non-physical quantities. Non-physical quantities. Non-physical quantities, on the other hand, cannot be measured. Okay, non-physical quantities cannot be measured. Example, you cannot measure something like patience. Hey, as for me, I have a great deal of patience. How will you measure how that amount of patience you have? Sadness. Okay, happiness, being annoyed. So these are quantities that cannot be measured. So we have physical quantity, whose quantity or magnitude can be determined, and then non-physical quantity which cannot be measured. Jeremy, your hand is up. You have a question? No. Okay. So dimensions, let me also add to what you said about dimensions. When we talk about dimensions of a physical quantity, dimensions of a physical quantity talks about the relationship the physical quantity has with the base quantities or basic or fundamental quantities. Let's then talk about the fundamental quantities. What and what do we regard as fundamental quantity? Ishra, 1.
So, sir, fundamental quantity, which is also known as the basic quantity, is a quantity which does not consist of any other quantity apart from that quantity only.
So they are on their own. So let's list them. One of them is,
yes, sir.
One of them is
mass.
Mass is
mass.
Mass does not depend on any other quantity. 2, you can yes, respond, sir, from wherever you find yourself. 2.
Time.
Length.
Length. I also heard
electric
time.
Current.
Temperature.
Time. Electric current. Electric current.
Amount of substance.
Yeah, okay. So 5.
Amount of
temperature.
Okay, temperature, amount,
luminous intensity.
Okay, so there are 7 in all.
Yes, please.
Amount of a
luminous
substance. Good. And then the 7th one is luminous intensity. Luminous intensity. Can we also quickly look at the instruments that can be used to determine these quantities? Mass. What instruments can we use to measure mass? Instrument to measure mass.
So please, a scale. Measuring scale.
Measuring scale, or in a laboratory, we mostly use the electronic balance. Yes, beam balance is an instrument for measuring mass, but it is not so popular. It is so Adamic, meaning it was used in Adam's time. Fortunately, in our time, it is used in weighing gold, diamond, and minerals. So it is not, though it's not common. Myself, I always see beam balance in TV and then in books. But the most famous instrument we have is the electronic balance. Okay, electronic balance. Then length. Instrument for measuring length. Theophilus.
Sir, please.
Sir, please. Caliper.
Yes, caliper, be specific.
Rule.
Because the calipers have specific usage. So the meter rule.
Sir, please, rule.
Yes, you are right. More instruments. The meter rule.
The caliper.
The what?
Vernier caliper.
Vernier caliper. Okay. These are for specific, we'll talk, you are not wrong, but they are for specific lengths, which we'll talk about. Then surveyor's tape. surveyor's tape, more instrument for measuring length.
Micrometer, screw gauge.
Yes, you see, I was talking about the calipers, being it micrometer, screw gauge, then the vernier caliper. They are for length, but the vernier caliper, for instance, is used to measure if you have a circular something, like something which is cylindrical, the milk tin fish container, and you want to measure the inner diameter. Then you go for the vernier caliper. So we use it for measuring inner and outer, okay, measurement. Evelyn, quiet, and your hand is up. Evelyn, your hand is up. Okay.
That is sewing.
Come again.
Sewing tape or teles tape.
Yes, the seamstresses tape. Yes. So we have a lot of them. Okay. Then the micrometer screw gauge. The micrometer screw gauge. Imagine being asked to measure the thickness of the sheet of paper. Just the thickness of a sheet of paper. And then you go in for a meter rule. How can you even determine it? Okay. So this is where the micrometer screw gauge, has its usefulness. Imagine you are asked to measure the thickness of your hair, and you are going for a surveyor's tape. Oh, okay. This is where micrometer screw gauge becomes useful. So the calipers, vernier caliper, they are for specific length. All right. Okay, time. How would you measure time? Please, let's respond.
Stop clock.
So stopwatch, the stopwatch.
Clock.
Clock. What again?
Hourglass.
A clock.
A clock.
Timer.
So wall clock.
Timer.
Come again.
Timer.
Timer. Wristwatch. All right. Electric current. Electric current. Go ahead, Evelyn.
Ammeter.
Ammeter.
Multimeter.
Multimeter. Okay. The prefix multi means it measures a lot of it is of lots of meters. So we can use multimeter as an ammeter, as a voltmeter, as an ohmmeter. That's why there is this prefix multi. Temperature.
Thermometer.
Thermometer. Thermometer. What again? Apart from the thermometer, what else can you use to measure temperature? But in our homes, if our parents wants to ascertain whether our body temperature is our body is hot or cold, they can also use their hand. They just touch our forehead. Is that not an instrument? Class?
There's an instrument.
Your parents will just touch your forehead. Your body is hot. Please give me a minute. I'm coming. One of us is calling me, Mr. Akpan. Hello. Yes, please give me a minute. Others are facing challenge logging in. Okay, so let me address their problem and then get back to you.
Okay, sir.
Yeah, Joe. Oh, this network issue. All right, so let's continue. Then, amount of a substance. How do we determine amount of a substance?
Sir, can you use pipette?
Okay.
Burette.
The pipette, burette, and anything which would determine the quantity that is being measured. Okay. Luminous intensity.
Please, photometer.
Photometer. Okay.
Light meter.
Photometer. Light meter. As for amount of a substance, we can get a lot of instruments to do that. All right. So these are the fundamental quantities or the base quantities. Okay. So dimensions of a physical quantity depends on these 7. However, at your level, we do not consider all the 7. At your level, we do not consider all the 7, but we express the dimensions of a physical quantity in terms of the mass, in terms of length, in terms of time. Okay, so please, if you are defining it, do not perceive dimensions to be expressed in only these 3. We can express dimensions of a given quantity in terms of all the 7, but at this level, we focus on only these three: mass, length, and time. Please, is that okay?
Yes,
Class,
sir.
is that understood?
Yes, sir.
Yes, sir.
Let me have feedback from everybody. All right.
Yes, sir.
So that is it. Is dimensional analysis or dimensions, okay, is very, very important in the measurement of physical quantities, as it enables us to determine some key information. One, what are the importance of dimensions of a physical quantity? What are the importance? What are the importance of dimensions of a physical quantity or dimensions? Yes. Otin Emmanuel. Otin Emmanuel. Hello, Otin. Importance of dimensional analysis. Okay, hello. Give us one.
Sir, please, defining the units.
So it helps to define the unit.
Yes, please.
Okay. So it enables us to determine the units of a physical quantity. There are more hands, so let me explore other, yes, participants. Jonathan Jordan, JJ Hammond.
It helps us to check the consistency of physical quantities.
So 2, it helps us to check the consistency or the validity or the correctness of a physical quantity. Then the third one goes to, okay, let me give the chance to Inshira Kwarteng. Inshira, the third importance of the dimensional analysis.
To find out what an expression stands for.
To find out what an expression stands for. This is
Yes,
so
sir.
open. Your response is so open. Can you break it down or be specific, more specific?
Like, it helps us to know what the expression is made out of.
Okay. Yes, more views. You can add more flesh to what has been said. If you want to explain what has been shared further, do that for us. Yes, so one, it helps us to, one, determine the unit of a physical quantity, mostly the basic unit of a physical quantity. Okay, when you know the dimension, you can also determine the unit of the physical quantity. 2, it also helps us to determine the validity or the correctness or consistency of a given equation. We'll look at all that. And the third one is that it establishes the relationship between two or more the quantity and other physical quantities. So it helps to establish an equation or the relationship between equations. Okay. Let me still respond to some colleagues. I'm wondering why others. There, your hand is up.
Yes, I have a contribution.
Okay, there you go ahead.
It assists in converting units of physical quantities.
It assists in converting units of a physical quantity. Okay.
Yes.
All right. Let's look at examples. We are going to pick the importance one after the other. So it enables us to determine the unit of a given quantity. So we are expressing dimensions of a physical quantity in terms of mass, length, and time. So dimension of mass represented as capital L, dimension of time as capital T, dimension of...
Sir, mass is capital M.
Sir, mass is capital M.
Oh, no, yes, you are right. Dimension of length, capital L, and mass, capital M. Mass, capital M. So, if I want to determine the dimension of velocity or speed, to determine the speed of an object, speed is distance covered over the time taken, isn't it?
Yes.
Class, is that correct?
Yes, sir.
Yes, sir.
Good. So to determine the dimension of speed, it means you must know the dimension of distance and divide this by the dimension of time. Dimension of time. Distance, the dimension of distance is L. The dimension of time is capital T, meaning that the dimension of speed is equal to L per capital T, isn't it?
Yes,
Now,
sir.
when you know,
Yes, sir.
when you know this, you can easily use this to determine the unit of speed. L is distance. What is the SI unit of distance or length?
M. Small letter M.
Small letter M. Per SI unit of time.
S. Small letter M.
S. Okay, giving us M meter per second. So what we've done is that we have used the dimension of the quantity speed to determine the SI unit of speed. So it goes to confirm the first importance of it, that we can use dimensions to determine the quantity of another physical quantity. All right. Work this out for me. Now, what is velocity? Class, what is velocity?
Displacement over time.
Displacement over time. Now, what is displacement? Class, what is displacement?
Sir, please length. Sir, please length.
Displacement is length. What is displacement? He has more views.
Length.
Displacement is not complete. To say length is partly correct, partly...
is the distance moved by a body in a specific direction.
Yes. So length, please, class. Length in a specific direction. Is that okay? Is that okay?
Yes, sir.
Example.
Yes, sir.
Let me give a practical situation. Right. I'm wondering why people are finding it difficult to join. I'm wondering why. Did you encounter any difficulty in joining the class?
No.
Because and I'm getting this message and I don't get the reason why. Okay. Okay, so supposing I move from a point A to a point B, and the distance from A to B is 10 meters. If I move from A to B and from B back to A, what is the total distance covered?
20 meters.
Please listen to the question. I moved from a point A to B. From A to B, the distance is 10 meters. Okay. If I move from A to B and from B back to A, what is the total distance covered?
20 meters.
20 meters.
20 meters.
Yes, 20. Do you know that if I want to determine the total displacement, it will not be the same as 20?
Yes.
For displacement, the total displacement will be 0. This is because for distance, we are looking at the total coverage. Okay, so A to B was the distance 10. B back to A was the distance another 10. So total distance will be 10 plus 10, 20. But for displacement, when I move from A to B is regarded as positive. And then B back to A is also regarded as negative. So it's like positive 10 plus negative 10, totaling what?
0.
0. So with displacement, it is a distance covered in a specified direction. So please, that is the difference. So velocity is displacement over time. If a body is moving and the direction does not change, displacement is the same as distance. Okay, but when the direction changes, because of the changing direction, displacement differs from distance. Are we okay? So this displacement over time. For dimensional quantities or dimensional analysis, distance and displacement have the same dimension. Okay, so the dimension of displacement L, the dimension of time T. So it means that speed and velocity have the same dimensions and so would have the same units. Class, are we okay?
Yes, sir.
Good.
Yes.
So the unit will still be meter per second. Now acceleration. Class, what is acceleration? When a body is said to be accelerating, what does it mean? When a body is said to be accelerating, let me give this to Lionel. Lionel Judah Atta.
Yeah, acceleration equals velocity over time.
You are right, but what is it? Lionel, I want you to explain to me what acceleration is.
Okay.
Okay. Let somebody else also come in. Jeremy Nielsen.
The rate of change of velocity.
Yes, Nielsen, you are right. But what does it mean? What does it mean? Can you give a practical situation? Let me go to the ladies. Let the ladies also come in. Henrietta, you are here. Kayla, you are here. Stephanie, over to you. Stephanie, can you give me a practical meaning of acceleration? Please give the chance to the ladies to also share their views, okay? Okay. Stephanie is quite Elom, go ahead.
Yes, sir.
Elom,
Sir, please, as they said that it is the change in the rate of velocity. So please, let's take the safety of cars, or maybe let's take cars. When a car is moving from a place to place, so please, you see, let's take its change of direction. Sir, please, are you there?
I'm here.
Sir, please, when it changes direction, yes, sir, please, the change of phase velocity is the acceleration.
All right. Let me also come in. Because of time's sake, let me come in. When you are stationary, what is your velocity? What's your speed? When you are stationary, what's your speed?
Zero.
Zero. Good. If you start walking or if you start moving, what is the speed?
1.
We can't say it's 1, but the speed or velocity is increasing. When you are stationary, is 0. But when you begin to walk, the value of the velocity will be greater than when you were stationary. Is that okay?
Yes, sir.
Yes, sir.
Now, when you start running, what will be the velocity compared to when you were walking?
Faster.
Or will be greater or faster. So look at the 3 different scenarios. When you were stationary, your velocity 0. When you were walking, your velocity increasing. When you begin running, your velocity would increase so much. So we see as the body moves from a stationary point to walking mode and then to running mode, we see the body's speed or velocity increasing with time, isn't it? Class, is that okay?
Yes, sir.
The body's speed or velocity increases with time. And when you have a body whose speed or velocity increases with time, we say the body is accelerating. Or when the body's speed decreases with time, it is also said to be accelerating. But in the decrease, we give it the term deceleration. All right. So acceleration is the rate at which the speed or the velocity of a body changes with time. Are you okay?
Yes, sir. Yes, sir.
Then a question to the class. The question is that, can we have a body moving all right, yet its acceleration be equal to 0? Can a body be in motion, yet its acceleration is equal to 0?
Yes.
How?
This happens when the object is moving at constant velocity.
When the body is at constant velocity.
Yes,
Okay.
like a car, like on the highway at a speed of 60 kilometers per hour without speeding up or slowing down.
Okay, I'm responding to, I'm coming, eh? I'm responding to something on the page.
Which school? Which school?
Me.
Okay, so as you said, yes, it will happen when a body is moving at a constant speed or velocity. So in school, during long distance events, when a runner is able to start with a certain speed and maintains it throughout, we say the athlete is very good. Why is the athlete good? Because he was able to start and maintain, start with a certain speed and maintain it till the completion of the whole race. Is that clear? So it will happen. Yes, Elom.
Please, is the direction also included?
So in this case, we are looking at the change in the speed, okay, with respect to time. Okay, there can be directions. There can be change in direction. That's why we are saying that acceleration is velocity with respect to time. Don't forget, velocity has to do with distance in a specified direction. Is that okay? So the changing direction can also be included here. All right. So let's look at using dimension to determine the correctness of a given equation. I have this WASI question, and what we are discussing. We are to use dimensions to determine the correctness of this equation. S is equal to U plus V all over 2 times T. And S is equal to UT plus V all on 2. Okay, we are asked to use dimensions to determine the correctness of this equation. So let's quickly go through it. So here, S is distance or displacement, and the dimension of displacement is capital L. U and V, velocity. There are two velocities. And the dimension, what's the dimension of velocity? What's the dimension of LT exponent minus 1. Good. Then T is time. Of course, the dimension of time is capital T. So to check the correctness of a given equation, it means that left-hand side equation or variables must be equal to the right-hand side variables. Please, is that okay?
Yes.
Yes, sir.
So L, for the left-hand side, we have L. Right-hand side, we have LT minus 1 plus another LT minus 1 all on 2 times capital T. So let's manipulate the right-hand side to see if it will be equal to the left-hand side. We can add the numerator. LT minus 1 plus another LT minus 1 will be equal to 2 LT minus 1, right? All on 2 times T. The 2 would cancel out, so we have LT exponent negative 1 times T exponent 1. Now, what is T exponent negative 1 plus T?
Please, 0.
That is
0.
That is what?
Negative 2.
I'm getting, I had 0. It is LT exponent 0. Okay, if you say 0, then you mean to say that the whole thing is 0. And any number raised to the power 0, apart from 0 itself, is equal to what?
1.
Is 1. Therefore, we have L is equal to L. What conclusion can we draw here? What conclusion can we draw here?
We can say, therefore, the left-hand side is equal to the right-hand side, which makes the equation valid.
Exactly. So if the left-hand side is equal to the right-hand side, then the equation is dimensionally valid, correct, or consistent. Class, are we okay?
Yes.
I want you to try the second question, this one. Give this a try. S is equal to UT plus V all on 2. Let's try and see whether the equation is dimensionally valid or not. Are you trying?
Yes, sir.
Yes, sir.
So, okay, I'm getting some feedback from you. Okay, so Derry has just submitted his answer. Who else? Yes, Derry, I'll talk about that.
So please, if I'm done, where should I put the answer?
Come again.
Where should I put the answer?
Oh, we'll discuss it. No, we'll discuss it. Don't worry.
Then we should put up our hand.
No, we will discuss it together. So don't worry. You mark yourselves after the discussion, okay? Class, can you hear me?
Yes, sir.
Yes, please.
Yes, sir.
Then let's discuss it. So UT, S is equal to UT plus V all over 2. You see the two equations are similar, okay? S is equal to UT plus V all on 2. So let's see if the equation is valid or not. S still remains L. U velocity. So LT exponent -1 times T again plus LT exponent -1 all over 2. LT exponent -1 times T straight away would give us what? L, isn't it?
Yes, sir.
Plus LT exponent -1 all over 2. You see, you cannot even add the numerator. They are unlike terms. Class, are you with me?
Yes, sir.
And once they are unlike terms for which you cannot add, straight away the equation, the left-hand side is not equal to the right-hand side. So equation is not dimensionally correct. Even though the two equations are similar. You see, this one, the first one is similar to the second one, but we cannot ascertain the validity. Class, are we okay?
Yes, sir.
Lionel, Alvin, please mute yourself, okay? Let's look at a third question. And I'm reading. Class, I'm reading. Pay attention and listen. The period of vibration, T. The period of vibration, small letter t, of a liquid drop. The period of vibration, small letter t, of a liquid drop is given by this equation. T is equal to K A exponent X rho exponent Y alpha exponent Z. So T is equal to K A rho exponent Y and alpha exponent Z. What looks like Y? Class, are you there?
Yes, sir.
Yes, sir.
Where K is a constant, we are told K is a constant, A is a radius. A is a radius. Rho is density. Rho is density. And gamma is the surface tension. Is the surface tension of dimension M T exponent -2. So A, rho, and alpha are defined. Now, class, listen to the question. Show by dimensional analysis. Show by dimensional analysis that T is equal to K times the square root of A cube rho over what looks like Y, gamma. This is a WASI question. WASI 2019. Okay, we have to show by dimensions that T is equal to K square root of A raised to the power 3 times rho over Y. So let's try it. I want us to quickly try it. Are we there? Class, are we there?
Yes, sir.
Okay.
Yes, sir.
So
Yes, sir.
T is equal to A, we are told is radius. The dimension is L exponent X. Rho, we are told, is density. And density is, what's the dimension of density? Class, what's the dimension of density?
ML
Please,
-3.
ML -3.
ML -3.
Okay. Isabella, that thing that has been said, okay. ML exponent -3. Then we put that into a bracket and raise it to the power Y. Gamma, we are told, is surface tension, whose dimension is MT exponent -2. So put this there. Okay, so we simplify. L exponent X, M exponent, the power affects all the dimensions under the bracket. So M exponent Y L exponent negative 3 times y, negative 3y. Class, are you following?
Yes, sir.
Are we? Okay. Times, yes, the power z affects everything under the bracket. So m exponent z, t exponent negative 2z. The next thing is that we group like terms. I want you to help me group the L's. Who will do that for us? Group, we are grouping like terms, but help me group the L's. The L's will be what?
X minus 3y.
X
Minus 3y.
good. X minus 3y. Thank you. Somebody to help me group the M's. M would also be
My
again.
my plus z.
So m to the power y plus z or z.
Yes.
Okay.
Yes, sir.
And then the t is a lone ranger. So t exponent minus 2z. Good. The next thing we have to do is to equate left-hand side to the left-hand side. And then t, we are told, is period. Period is time. So capital T is equal to L exponent x minus 3y times m y plus z times t exponent minus 2z. So we can equate the t's. All right. So it means this is to the power. So t is equal to t exponent minus 2z. This is equation 1. And we can conclude that the powers minus 2z is equal to 1. Therefore, z is equal to negative half. Class, are we okay?
Yes, sir.
The ladies, are you there? Abbas.
Sir.
Abbas, your
Sir.
hand is up. Hello.
Sir,
Go
please,
ahead.
yes. Sir, please, I don't get it. Can you please go over it again?
Okay,
Like
so
from equation 1. Can you please go over it again?
okay, so over here, I think you're okay with this part, isn't it?
Yes, please.
So we are equating letter by letter. So we are first equating the t's. So t exponent 1 is equal to t exponent negative 2z. Are we okay?
Yes, please.
So the power of the right-hand side t, which is negative 2z, is equated to the power of the left-hand side t, which is 1. So minus 2z is equal to 1. Then we find z by dividing 2 by negative 2.
Okay.
All right. Then
Thank
we equate, you're welcome. We equate the L's as well. You see, we don't have a component of L at the left-hand side. Okay. But what we can do is that when we multiply t by 1, have we changed anything at the left-hand side? When we multiply t by 1 at the left-hand side, have we changed anything? No. So we can say that L exponent x minus 3y is equal to L exponent 0.
0.
Meaning we can modify this one to be L exponent 0. This is because L exponent 0 is equal to 1. So we can equate the exponent. X minus 3y is equal to 0. Class, and this is equation 2. Class, are we okay here? Abbas, are you fine?
Yes, please.
All right. Let's equate the m's. That will help us. Since we have z, we can find y. Israel, your hand is up.
It's okay. I've seen.
Okay, can I continue?
Yes,
Okay, so let's equate the m's. Right hand side m, which is exponent y plus z, can be equated to left hand side m, which is what? Can somebody help?
M exponent 0.
M exponent 0. Thank you. M exponent 0. Because M exponent 0 does not change anything at the left hand side. The value is still the same. And this would help us equate the powers. Y plus Z is equal to 0. Since we have Z, we can find Y. Okay, so please go ahead and help me find Y. When you finish, go ahead and find Z. X. We have Z. We can find Y. When you find Y, go ahead and find X. So continue. Please, everybody should be involved, okay? Just give it a try. Do not be isolated. Kekeli, can you hear now? I just saw your message that you cannot hear. Can we continue?
Yes, sir.
Yes.
Okay. So
Yes,
what did
sir.
you make for? What did you make for Y?
1/2.
1/2.
You had 1/2. Let me confirm 2. So since Z is negative half, Y will be equal to 0 minus Z. Okay, so 0 minus, then Z is negative, so it will be minus half. Therefore, giving us Y is equal to 1/2. Thank you. So I'm sure all of you got half.
Yes, sir.
All right.
Yes, sir.
Let's then, hey, who is writing on my board? Justice. The board is for me. Oh. All right. So let's find the other variable using equation 2. X minus 3y is equal to 0. Since we have y, we can find x. So what did you make for x?
3/2. 3/2.
Okay, 3y. And y is
3/2.
half. Good. So x will be 3 over 2. So let's substitute. We have to show this. So let's substitute our values. T is equal to a exponent x. Hey, I have this board. Let me clear this and use this instead. So T is equal to a exponent x rho exponent y and gamma exponent z. T, therefore, k shouldn't be omitted. So k is equal to, this is k, a, what did we make for x?
3 over 2.
3 over 2. So put that there, 3 over 2. Then y, what did we make for y?
Half. 1 out of
We had half. 1 on 2. And then z minus half, isn't it?
Yeah.
So we are manipulating this to prove this. So let's see how we can do that. Justice.
Yes, sir.
Your hand is up.
Yes. Sir, please, I don't understand anything that you are teaching. Oh.
Oh.
I just came right now. So, like, it is difficult for me to understand.
I get you. So what I'll do is that, I'm sure you did dimensional analysis in school, right?
Yes. Yes.
So I'll forward, when we finish the lesson, just give me a hi or a message. I'll forward the video to you.
Okay.
All right. So since this exponent have Abbas.
Sir, please can you forward the video to the group platform, because I also want to go over the lesson.
I'll do that. I'll do that for all.
Okay. Thank you.
Welcome. So y exponent negative half is equal to 1 over this. And so we can re-express this as t is equal to k a exponent 3 over 2 rho exponent half divided by gamma exponent half. And so we can represent this. Okay. If you have a exponent 1 over n, it is the same as a exponent 1, then you take the root of that number here. So root n a raised to the power 1. Because using this, we can express a as square root of a exponent 3 times, we can express rho density as square root of rho exponent 1.
Sir, please, I'm not in the... Sir.
I'm listening.
I'm not in the group. I just joined it right now. So please, can you add me to the group and I'll record, and I'll get the recording.
Okay, now they take my number, and after the class, give me a message. Okay, 024-096, another 0965. It's class. This is my number. You can contact me anytime. Okay. 024-096, another 0965. 024 class general. That's my number. 096, another 0965. I hope that's okay.
Okay, thank you.
Welcome. So we can also represent the denominator as square root of y or row exponent 1. The square root is common. Therefore, it means that we can bring all of them under the same square root umbrella. Okay, so k root of a exponent 3 times rho over this. Haven't we proved what we were asked to do? Yes. So
I want to ask a question.
Go ahead.
Please, what if you leave it as t is equal to k a3, like what you did before you change it to this one? Like
you
if
mean
you leave it,
you mean this part?
Yeah. Yes, please.
When you leave it like this, I'll take some coins out of your money, meaning that I'll deduct some marks, because ideally you are to come to this point. Are you okay?
Yes, please.
Meaning you couldn't get to your destination, so I will take some coins. Is there any other question? Class, is there any other question if you don't understand some aspects of what we've done? Or we can move on. All
Yes,
right.
sir.
I actually
Yes,
intended
Yes,
giving
sir.
this to you as an assignment. Unfortunately, I've solved it with you, and I'm not happy. And I'm not happy at all for solving this with you. I would have loved to see how you can weave your way around it. Okay. But let me still look for another. So please, this is how we tested the uses of dimensional analysis. We earlier used it to determine a unit of a given quantity, then test the validity, and we have now used it to derive equation between quantities. All right. But you know dimensional analysis have limitations. Dimensional analysis have limitations. So let's look at limitations of dimensional analysis. Who can help me explain the meaning of the word limitation? Who can tell us the meaning of the word limitation?